Hello everyone, this is Dr. Webb. Now we are moving into the next big area in our course, and that's thinking about multiple integrals, or integrals in multiple dimensions. So we're going to start off easing into this, and we're going to focus in on double integrals, in particular double integrals over rectangles, over rectangular regions. Okay, so here's the setup. We have a surface z equals f of xy, and we want to find the volume under that surface and above some rectangle on the xy plane. And so then the rectangle is defined by a interval for x and another interval for y. So let's draw a picture of exactly what's going on here. So here are our axes, and here's our surface going on here. So this is our f of xy equals z. Okay, so we're building a rectangle where the x values are coming between a and b. So these are kind of cutting across this way. And then our y values are coming across C and D. So they're cutting across that way. And so we have this nice rectangle right there. And then this is kind of going up and curving, cutting out a volume that goes up to the surface. And so where the top of the surface is on f of xy equals z, and the sides look like sides of a box. Okay. So if you think back about starting off integration in Calc 1, a lot of what you do at the beginning is you focus in on, in Calc 1, you're focusing in on the interval that the x are going through and breaking that up. We're going to do the same thing, except now our region on the bottom is going to be a rectangle instead of just some straight line. Okay, but we're still going to approach this the same basic way, right? So we're going to build a Riemann sum to do this. Right? And so let's start off, we're thinking about our region doing this. So we're going to look at the base on the xy plane. And so let's try and use colors. So here are our x values going from A to B, our y values going from C to D, giving us this nice rectangle. Okay, and now we're going to do the exact same thing that we did in Calc 1, except now we have to do it for both x and y. So what I mean by that is we're going to break this x interval, let's break it up into n subintervals. These are each going to be delta x wide. And so break, 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 break. There's n of them. Slice it up this way. And then we're going to break the y into, let's say we're going to break this into m subintervals. And these are each going to be delta y wide, delta y long. And so say we do it like that. These are all the same width, something like that. Okay. And So if we zoom in on one of these boxes, let's zoom in on it. So let's say that this is the ith interval in terms of x and y, and this is the jth interval in terms of y. And so this box is going to look like, making it bigger, so this box is delta x wide, delta y high, and so we have a little bit of area here. Let's call it delta area. And because this is just a rectangle, that area here is just going to be delta x times delta y. Okay. So we've broken up, we have our base now. Right now, if we want to do the volume over this little square of area, well, we have the area of the base, we just need a height. So how are we going to pick a height? Well, we're just going to pick some point on here. And in fact, what we'll do is we'll actually pick, for each interval, we'll pick some x value. We'll call this x1, x2, let's call this one, since we're in the ith interval, xi. We'll do the same thing in the j and the y's. And so for this one, we'll pick some, well, it looks like I'm picking it up there. We'll call this yj. And so this coordinate here will be xi, yj. And so then when we look at this down now in the what's happening in 3 space, so let's see, green now should be going the other way. So we translate this to 3 space. We're going to have our little box here. In 3 space, we have our surface kind of going up above it, and we're picking our point roughly right there. And so that's going to give a height of f of xi yj, and that then is going to give us our box. Where the area of the base is this delta x, delta y. The height is f of xi yj, so f evaluated at xi yj. And so then this little bit of volume here over this, let's call it the ijth box, is approximately, take the height, f of xi yj, and multiply it by the area of the base, delta x, delta y. Okay, and now we're going to repeat this over every single square in the region. Keep going through, get estimates for volumes over each one, and then how do we get the total volume? Same as in Calc 1, we're going to add these all together. Now the thing to note is that we're doing this sort of as a rectangle, and so we're going through and doing all the x's, and then we're also going through and doing all the y's. So there's both, as I'm going through here, I'm doing x's and then doing y's. Okay. So putting this all together to get the total volume, we're going to get something that looks like this. Okay, so this f of xi yj delta x delta y, this is representing the volume over the ijth little rectangle. Okay. And then we want to add this together over all the rectangles. And so if you think so the way to kind of read this, this is what's called a double sum. And so we have one sum nested inside of another sum. And so the way that you can kind of read this is the first sum is in terms of the i's. And so the i's are corresponding to x. And so this sum we are adding over the x's. And you can think that we're keeping yj fixed. Right? And so if we're thinking about the box going through here, for each yj, we're adding up everything in that. So we do all of y1. Then we go next and we do all of y2. Then we go next and we do all of y3. Then we go next and do all of y4. And we keep on doing that until we get all the y's. And so we do all these sums individually for each y, going through all the x's. And then we do the outer sum. And in this outer sum, that's when we're then adding these y's together. Okay. And so that's how you should read this. So you read these sums from the inside out. Well, so if you look, this looks an awful lot like the Riemann sums that we saw in Calc 1. And so in particular, if we just focus in on the inner one, in fact, the delta y, that's a constant. It's not really changing in terms of x at all. And so we can just pull it out and focus just on the delta x's. Well, then if we let n go off to infinity, so n being the number of boxes we have, n being the number of subintervals we have in the x direction, so having n going off to infinity, this is the same thing as having delta x go to 0. Then this is exactly the same thing that we saw in Calc 1. And so we can write this as an integral. And in this integral, if you notice, the x's have changed, but we're not touching the y's at all. And so the yj's are still there. And in fact, in all of this, in this integral, we're treating yj as a constant. And we're integrating in terms of x, right? And so we read this integral as we are integrating x, starting at a and going to b. And in doing this, our variable of integration is x, the yj's are constants. Okay. So then we go through and do this, and this, if you notice, this is a definite integral. In terms of x. And so if it's a definite integral in terms of x, after we do this integral, all the x's will be gone. All that will be left will be all of these yj's. And so after the integral, after the inside integral, we'll end up with something that looks like this, and it will be some new function, but now it's a one variable function only in terms of the yj's times the delta y. Well, this now is exactly, looks like a Riemann sum that's just in terms of y, and so we can, if we take m going off to infinity, we can integrate this the same way. Right, and so this g yj here, this is what we get by doing this definite integral. And so then if we let m go to infinity, then we have what we got from doing the inside integral. After we do that, everything's just going to be in terms of y. And then we integrate that in terms of y with the bounds going from y goes from c to d. Okay. And so, as you can see, the way that when we actually do these, we're actually going to be dealing with integrals that look like this. And the way this is written, we are doing, you read these integrals from the inside out. We're going to be doing an integral in terms of x first, where the bounds are x equals a to x equals b. Do that definite integral. Plug in the bounds at the end. Everything in terms of x is going to be gone. All that we're going to be left with is in terms of y. And so then we do an integral in terms of y, where the bounds are now y equals c to y equals d. And then at the end of that, all of the y's are going to be gone. And so all the variables are going to be gone, and we're going to be left with the volume. Okay, so that was a lot of me talking very generally about this. Let's actually do a concrete example and see how this actually works. Right, so our function here is x cubed plus 2xy squared plus 4y, and we're doing it over the integral, doing it over the rectangle where the x values are going from 2 to 3 and the y values are going from 1 to 5. So following what we had before, we have our function, x cubed plus 2xy squared plus 4y. Okay. And then in the way we were setting this up, we talked about doing the integral in terms of x first. So let's set that up. And so our integral in terms of x, and so let's use green to talk about our x values. And so this is going to be, we're doing the integral in terms of x, where the bounds are going from x equals 2 to 3. And so let's work this out. What do we get from doing this? So I'm integrating in terms of x, treating all the y's as constants. Okay, so x cubed goes to x to the 4th over 4 plus 2xy squared. So the 2y squared, that is a constant. And then I'm integrating x will give me x squared over 2. And then lastly, I'm integrating 4y, so that's just a constant. Integrating a constant would give me 4yx. And then we do these bounds from 2 to 3. And so what do we get out of doing that? So I can cancel off these 2's. So 3 to the 4th over 4 is going to give me 81 to the 4th. Plus plug in 3 for x squared, so then I'll have 9y squared, plus 3 for x there gives me 12y. That's what I get for plugging in 3. Then I subtract off what happens when I plug in 2. 2 to the 4th is 16 divided by 4 gives me 4, plus 4y squared plus 8y, right? And then I think we can simplify this down a bit more. So 81 over 4 minus 4, so 4 is 16 over 4, 81 minus 16 is 65. So we have 65 over 4 plus, I have 9y squared minus 4y squared, so that's going to be 5y squared, and then 12y minus 8y gives me plus 4y. And so notice now this is only in terms of y. All the x's are gone after we do that double integral. And so now we can do the second integral in terms of y. And so that integral is going to be going from 1 to 5 of 65 over 4 plus 5y squared plus 4y dy. So now this is only y's in there. This is just a regular Calc 1 integral. And so this is going to be 65 over 4 times y plus 5/3 y cubed plus 2y squared, going from 1 to 5. And so, let's see, 65 over 4 times 5 minus 1 is going to just give me 65 plus 5/3 times, let's see, y to the third is, or 5 to the third is 125, minus 1 gives me times 124. And then plus 2 times 5 squared is 25 minus 1, so that'd be 2 times 24. And I don't know if there's all that much. 2 times 24 is 48. This is whatever it is. I don't want to go through and figure out exactly what it is. Actually, no, let's leave that how it is. And so there's our value. So we did this all in terms of doing integrating in terms of x first and then integrating in terms of y. What happens if we reverse this? So let's clear this out and let's think about doing this the other way first. Okay, so if we go back to the beginning and we do this in terms of y first, so we have our function 2xy squared plus 4y, but now we're going to integrate it in terms of the y values first. Okay. And so we're going to treat all of the x's like constants. So this is going to be x cubed y plus 2/3 x y cubed plus 2y squared. And the y values here are going from 1 to 5. And I think I'm going to end up with 4x cubed plus y cubed is 125 minus 1 is 124. So 124 times 2 times 124 is 248 over 3x plus 2y squared, 2 times y, so 2 times 5 squared minus 1 squared, so that's going to be a 48. And so now this function is just in terms of x. And so then we can go through and do the integral in terms of x. So the integral in terms of x, the x values are going from 2 to 3. 4x cubed plus 248 over 3x plus 48. We're integrating in terms of x now. And so if I do 4x cubed in terms of x, that's going to give me x to the fourth plus 248 over 3 times x, so that's going to be 124 over 3x squared plus 48x. And we're doing these from x equals 2 to 3. So what do we get at the end of this? So 3 to the fourth is 81 minus 16. 81 minus 16, we already did that. That's 65 plus 124 over 3 times 3 squared is 9 minus 2 squared is, so 9 minus 4 is 5. Plus, at the end, we have 48 times 3 minus 2, which is just 48. And so if you go back, this is exactly the same thing that we got from before. So same as before. And so the order really doesn't matter here. And the order in which we do this doesn't matter. Okay. So let's talk a little bit about, if you're just given this double integral, how to read it. Okay. And so we talked about this before. So you read it from the inside out, right? And so the inside bounds go with the inside dx. So we have, so these bounds, a is talking about a, x is going from a to x equals b. And we read that because we have dx on the inside. So the inside ones go together, and so then this is saying that we're integrating x first. And then after we integrate x, then we're integrating in terms of y, and these outer bounds match with the outer measure, the outer dy. And so these bounds are in terms of y. So the y values are going from c to d. And so then we're integrating y second. For rectangles, the order in which you do these don't matter. And so in fact, you can just flip them, so long as you're flipping both the integrals and the measures on the other side. So what I mean by that is you have dy is matching up with the inner integral going from c to d. So this is saying c and d are in terms of y. And then the outer integral is matching up with the outer dx. And so this is saying that the a values, that the x values are going from a to b. So if you flip them, you have to flip both the integrals on the left and the measure variables on the right, so the dx, dy. And so the AB is still matched with the dx. The CD is still matched with the dy. As long as those are matching together, you're going to get the same thing. The order in which you do it doesn't matter. Okay, so let's close this out doing one more example of going through and doing this integral. So now we're doing the integral of, where our function is y times sine x, and we're doing it over the rectangle where the x values go from 0 to pi over 2, and the y values go from minus 2 to 1. So let's do this in terms of x first. So I'm going to keep writing these as separate integrals just to emphasize that we're doing one variable and then the other. And so we're integrating y sine of x dx from 0 to pi over 2. We can treat the y as a constant, so we can just pull it out. The integral of sine is minus cosine, where x is going from 0 to pi over 2. And so cosine of pi over 2, well, that's 0. So this is minus 0. And then minus minus gives me a plus. If I plug 0 into cosine, I get 1. And so this inner integral just left me with a y. And so then to do the outside integral, I'm just integrating y from minus 2 to 1. And so this is y squared over 2, going from minus 2 to 1. So at minus 2, this is, so if I plug 1 in, I get 1/2, and then minus plugging minus 2 in, it's going to give me 4 over 2, and so this is minus 3/2. Okay. And so that's doing x first and y second. So remember that we get minus 3/2 out of this. Let's try doing it the other way. Let's try and erase this in a responsible way. There we go. Okay, so if we do this in the other way, so we're doing y sine x, but now we're going to integrate in terms of y first, and the y bounds are minus 2 to 1. So the sine x here can be pulled out, and so then we're integrating just y, which would give me y squared over 2, as y goes from minus 2 to 1. Plugging that in, this is going to be sine x, so 1 gives me a half, minus 4 halves, so we're going to end up with the minus 3 halves again. Right? And so that's what we get in terms of that. All of the y's are gone. We're left just with a function of x. So now we can integrate this in terms of x. And so now we're integrating from 0 to pi over 2 of minus 3 halves sine x dx. So the minus 3 halves can get pulled out. Integral of sine is minus cosine. Going from 0 to pi over 2, same as before, it's going to be 0 minus minus 1, which gives me a plus 1. And so we get minus 3 halves, same as we got before. So order really doesn't matter. That is all I have for you for this video. I will see you again soon.